All right. So for our first lecture, we've got systems of linear equations, where linear algebra really starts. And it's going to start off very basic. As I was mentioning at the beginning of class, a lot of this stuff you might have seen in high school or middle school. So we'll get through it in a couple days and then start to move on to more advanced stuff, more advanced techniques. So systems of linear equations, I don't want to write all of that out. I might just abbreviate it. Systems of linear equations, or maybe put EQ there for equations. So we're going to start off with the geometry of systems of linear equations. So system of linear equations is just a set, a collection of linear equations. So linear equations in calculus and pre-calculus, hopefully you've learned, are just lines in 2D. So for example, we can have one linear equation representing a line. We can have another linear equation representing another line. And then we see that they intersect at one point. So this is two equations, one solution. So a solution to a system of linear equations geometrically is going to be a common intersection point for all equations in the system. Now, we don't always have a solution. So geometrically, we can always draw lines that are perpendicular. And there also are certain cases where we have an infinite number of solutions. Namely, if I have two lines, I can write the equations maybe slightly differently, but I have two equations that represent the same line, and these two lines are over top of each other. And then here we will have infinity solutions. In 3D, so let me know if I flip a page or something like that, if someone's still writing. Speak up. Let me know if I go too fast through the notes. If you guys are writing, I don't want to leave you behind. So 3D, well, what's going to happen now? In 3D, a system of linear equations, or a linear equation in three variables, is going to give us a plane. And so what we are looking for in 3 dimensions are the intersection of planes. So for example, we could have the xy plane, the xz plane, and then maybe the yz plane. So it sounded like most of you guys have had Calc 3, so most of you are probably familiar with that terminology. If you have not had Calc 3, essentially what we are doing is extending the Cartesian plane, the xy plane, and now making it a three-dimensional space. So we have three axes, our x, our y, and then our z is the vertical axis. And so when I say something like the xz plane, that's the red plane. It's the plane spanned by x and z. Likewise, our yz plane and our xy plane. Now these have common intersection points. At the origin. So 0, 0, 0. We would call this the solution to the system of linear equations defined by these three planes. Now, weird things can happen in 3 dimensions. Sometimes there are no solutions. So for example, we could have the xy plane at the bottom, and then we could have a plane that is perpendicular to the xy plane. And we could even have a plane that intersects both of them. So let's say we have a plane that goes vertically. And we could see that there are intersections between these planes. Any pairs of the green and one of the other planes intersect, but there is no solution, no points on the intersection of all three. So when we say a common solution, or when we are looking for a solution to a system of linear equations, geometrically, it means that we're looking for a point, or possibly a set of points, that are on each geometric object defined by each equation. So we can't have things like infinite solutions. So again, let's start with maybe the xy plane. But then we can also have planes that are maybe rotated about. If we rotate the xy plane towards the z-axis, if we are rotating this upward, we can maybe have a diagonal plane So maybe this plane here is sitting at 45 degrees rotated up from the, sorry, let me try to draw those angles better, rotated up from the xy plane. And then we might have the vertical plane, the xz plane. Where here, there's infinity solutions. And our common solution is the x-axis. So there's an infinite number of points where they intersect, and we just can describe the points of intersection by a line, by the x-axis. So these are our geometric examples. 3D, we can see there's only one way we can have one intersection point, namely if they all intersect in one point of intersection. There's going to be a lot of different ways where we might have no solutions. I could have 3 parallel planes. I could have 2 parallel planes with some slicing plane. And then for infinity solutions, we have these axes. And then these examples are going to generalize. So of course we will be moving on to 4-dimensional, possibly 5-dimensional, or any arbitrary dimension in terms of the number of equations we're going to be looking for. So geometrically, essentially what we're doing, if we're in 3 space, our linear equations define 2-dimensional objects, namely planes. If we're in 4 dimensions, then our linear equations are going to define 3-dimensional objects. So there's going to be 3 spaces within a 4-dimensional space. And the way that each of these spaces can intersect when we have a system of linear equations essentially is going to grow with the number of dimensions. So what we need is a better algebraic tool to work with these guys. So let's take a look. Let's get into the actual algebra now behind what's going on with these guys. Algebra of the systems of linear equations. So a system of linear equations is essentially an array of equations. So it looks like this: a11 x1 plus a12 x2 plus a1n xn is equal to b1. a21 x2 plus a22 x2, sorry, x1 here, plus a2n xn is b2. And we're going to keep going. So however many equations we have, a m1 x1 plus a m2 x2 equals b, bm where each of these a, I, j are an r. So if I write this, a, I, j, this sort of sideways script e means an element of r, just means real numbers. And the b, I are also real numbers. So these are called scalars. Or coefficients, or coefficient scalars. And the bi are just constants. So how's this notation? Is this familiar, confusing to any of you guys? Linear algebra might be the first course you've had where we start to use multi-indices along with independent variables that are now numbered instead of just using different letters. So in finite dimensions and small dimensions, we often like to use X, Y, and Z. If we were in 3 dimensions, if we were in 4, we'll use X, Y, Z, W. But if we have a large number of dimensions, we usually represent our independent variables by all x's, and we'll just call them x1, x2, x3. So in 2 dimensions, if you think of it as like x1 and x2, you can think of it as x and y, and then our dependent variable would be z. These aij are our coefficients, our scalars, and we always index them by row and column. So aij, it's always the row by the column. Just to keep them in order. And this will apply once we move into matrices. So you can kind of see as we move over the column, A1, 2, move over the column, next one's 1, 3. And if we move down a row, A1, A2, 1, A2, 2, etc. So this is a system of linear equations. We do have another form. I don't want to write it all out, but if all of the BI are equal to 0, we call it the homogeneous system of linear equations. So same array, except now just zeros on that right-hand side of the equal sign. Call those homogeneous. A system of linear equations is called consistent if there is at least one solution. Inconsistent if no solutions. Any questions so far? Okay, so that's kind of the math behind it. Let's get through examples. And then how do we work with systems of linear equations? So basic example to start with is just verification problems. So for example, we can have a system of linear equations of here. So let's say verify that xy equals -1, 4 is a solution to the system of linear equations x plus y equals 3 and y minus x equals 5. So again, we're in low dimensions. We've only got 2 independent variables, so we'll just use x and y for those guys. How do we verify that something is a solution? Well, geometrically, a point is a solution if it is on each equation, if it is on each line defined by each equation. In other words, if we plug in the point to equation 1, we get a true statement. So this point is on the line defined by equation 1. We check point 2. or check equation 2 with the same point. And of course, again, we get a valid statement. So minus 1, 4 satisfies both equations. Meaning it will be a solution to the system of equations. Now, in general, if we have more complicated systems and we actually want to find the solution, we want to do what are called elementary operations, which we will actually extend. We'll call these elementary row operations once we define things by matrices. So what are our elementary operations? We've got 3 things we can do. We can switch the order of equations. We can multiply an equation by some non-zero element. Or 3, we can replace an equation with the sum of itself plus a scalar multiple of another. So there are some other methods that you've probably learned. So for example, if we had this system of equations, we could do what are called substitutions. Namely, I could solve equation 1 for x, so x is equal to 3 minus y. And then I could plug in that 3 minus y into the x value into the next equation. And that would result in solving for y. So that'll work. However, those methods don't work very well once we get into 3 or more variables. That process seems to take a lot longer. And so what we're going to end up doing is using these elementary row operations to solve all of our systems of equations. So for example, I think we'll have enough space. Let's see. Let's try to fit it in here. I've got x plus y equals 7 and 2x minus y equals 8. So I'll try to label the equations at the moment just so we can write out the steps and you guys can follow that a little more easily. Now we can always switch the order, multiply by a non-zero if we want to, or replace a given equation with the sum of itself plus a scalar multiple of another. We're going to take advantage of this third one quite a bit. So our process for solving these is essentially what we want to do is get rid of some of the variables. Pick one of the variables at the beginning and try to eliminate that from our systems of equations. So namely, if we replace 2 with the sum of 1 plus 2, then we are going to have a new system of equations. First one's going to stay the same. The second one now, let's call this 2 prime, our new equation 2. I add these two together. So what are we going to get? Well, when I add my x's, we'll get 3x. And now nicely enough, when we add those two together, there are 0 y's. And then we add the right to get 15. And now what we can do is replace two prime with, say, 1/3 times 2 prime. In other words, we're going to multiply both sides of that equation by a third, dividing by 3. So our new systems of equations, x plus y, sorry, I wrote a 7 there, equals 7, and then we will get x is equal to 5. And so once we've isolated one of the variables, we can now proceed as we would with our substitution method by simply plugging that 5 back into 1. And what do we get? Our y value is 2. So our solution is 5, 2. Check that. I would also highly recommend going back and checking your work with a lot of these problems, especially on exams, quizzes. Plug that number, plug 5 and 2 in for x and y. Make sure that we get valid statements for each of the equations. It's real easy to make algebra mistakes with a lot of these, especially as the variables get larger. So if I end up making any algebraic mistakes, feel free to speak up. Let me know if I copy something down or miss a multiple of 2, miss a minus sign. All these things, kind of common arithmetic mistakes, are going to be the most common things, common mistakes at this point. Let's do one more example. We've got a bigger example. So we've got x plus 3y plus 6z equals 25. We've got 2x plus 7y plus 14z equals 58. And we've got 2y plus 5z is equal to 19. So one of the things you're always going to want to do is make sure that your independent variables are lined up. And one of the previous examples we saw, the first one we started with, here it was y minus x. When we want to do row operations, you want to make sure the variables are lined up above each other. So this first column should be all of our x's with our x coefficients. Next column should be y's. So we may want to rearrange this second equation as minus x plus y if we want to do row operations. Nicely enough, in our next example, they were already aligned. And with most examples, they should already be lined up. And if you want, you can always fill in necessary zeros for the terms that are missing if you'd like. So let's go through this one a little more quickly. We've got 1, 2, and 3. And so our process is going to be to eliminate the variables one at a time. Let's go ahead and eliminate our x's since this one doesn't have an x. So let's go ahead and do 2 times equation 1 and then add it to equation 2. And actually, let's do a minus 2 times equation 1. Add it to equation 2. So what are we going to get? We're going to have 2 times equation 1 plus that guy. The resulting equation, I'm going to replace equation 2 by. So I'm just going to write it out like this. So let's just do the work. Minus 2 plus x will give us 0x. Plus we will have minus 6y plus 7y gives us 1y. We will have minus 12z plus 14z gives us a positive 2z. And then we've got minus 50 plus 58 gives us positive 8.
I'm sorry, can you repeat why you did the -2 again?
Yeah, so we are looking to eliminate the x's. So right here, I've already got 0 x's. You want to look to eliminate one of the variables in all of the equations except for one. So this equation already has an x in it, and we like a coefficient of 1. Coefficient of 1 is easy. This one has a coefficient of 0, so this one we don't have any x's, but this one has 2 x's. So maybe we can come up with a new equation for 2 that has no x's in it. How do we do that? We look for, well, equation 1 only has 1x, so if I multiply this equation by -2, it'll give me -2 x's. And then when I add it to this guy, -2 plus 2 will give me 0 x's.
Oh, I see, I see.
Yeah. Then you just compute how are all of the other variables affected. And so this guy's going to be our new equation. We'll call it 2 prime, or you can call it 2b if you want to relabel them with numbers or something like that. And so our new system, we've got x plus 3y plus 6z equals 25. And now this one, there's no x's. We've got 1y plus 2z equals 8. And then the third one, we've got 2y plus 5z equals 19. And so we've got our 1, our 2 prime, and equation 3. Here. So I try to box my work. Put little sort of corners just to organize different statements and different sections that I'm working on. So now the solution to this system of linear equations is equivalent to the solution of this system of linear equations. So now what we want to do is look to get rid of some of these y's. We have one equation with a y in it, so we have to keep at least one. So let's go ahead and keep this one. Again, because we like that coefficient of 1. Coefficients of 1 that appear at the beginning are really nice. We'll formalize this a little bit more as we move into matrices. So what we're going to do is get rid of the y's in equation 3. And we can do that fairly easily because there's a 1 here. So whatever this multiple is, in equation 3, we see we have 2 y's. So if I just take -2 times equation 2 prime, again, that'll give me -2 y's in that equation, so that when we add them, the y's here will vanish. And so what are we going to get? We will have -2y plus 2y, gives me those 0 y's. We will have -4z plus 5z, gives us 1 positive z. And then -16 plus 19 gives us 3. And so we're going to use this equation now to replace equation 3. And of course, simplifying that, we just get z is equal to 3. So we found our third variable, z. And now nicely enough, since these two equations don't have x's in them, if I plug that z into either of these equations, we can figure out y. So if we do our 3 prime and then substitute that, stick that into equation 2 prime, we're going to have y plus 2 times 3 equals 8. So y is equal to 6. Now we know z and y, and we only had one equation that had our unknown x's. We can plug in our z and y's into that one. So we can say z is equal to 3, y is equal to 6. Plug those now into equation 1. And what do we get? X plus 3 times 6 plus 6 times 3 equals 25. So 18 and 18 is 36. And so x is equal to negative 11. So check that on your own, plug in those values into the original system, see if each equation gives us a valid statement, valid equality. Unfortunately, I don't want to spend too much time checking a lot of these because we do have quite a bit to get through. Okay, so I kind of just mentioned it as we were working, but the theorem is elementary row operations or elementary operations don't change the solution set. To a system of linear equations. Which is why we like to do them. We saw that process of eliminating variables one at a time. And by doing that, we're not changing the overall solutions, but yet we're coming up with a more simple system of linear equations. And ultimately, our last equation, the most simple one, we found a solution for one of the coordinates, z is equal to 3. And then once you have that, you can back substitute to find the rest. So let's take a look at how we want to do these with what are called matrices. So we'll be working with matrices more tomorrow. For now, we'll say that a matrix is a rectangular array of numbers. So what we can have now, when we have a system of linear equations, I'm going to write it in our abstract notation. All the way down to AM1, X1. Since we have linear equations, the key thing about the word linear is that our independent variables are all of degree 1, right? We don't have any x squareds, we don't have any y squareds, no z squareds. And of course, if we have multiple independent variables, there's no quadratic terms, no cubics, no tangents, no crazy functions, all just degree 1. So we can, in some sense, just get rid of those and not write them out and simply write our matrix as the coefficients, because the coefficients were really what determined everything about this system. So I'll write out another row, A21, A22. And our matrices, we like to just put in square brackets. So this guy is called our matrix of coefficients. If we put all the terms on the right at the end, this is our matrix of constants. And then we will commonly see these together. So A11, A12, all the way up to A1n. Then we often put like a bar here to separate the constants. This is what's called our augmented matrix. So it might be just called the augmented matrix, or we could call it the augmented matrix corresponding to the system of linear equations. So there's no operations written in between here, just spaced by whatever the coefficients are written. So it's a list in some sense of all of the objects that we care about, except it's a sort of two-directional list. We have a right direction and a down direction. So two positions that define the coordinates. We'll talk a lot more about matrices and matrix algebra tomorrow. For now, let's get into our row operations on augmented matrix. So for example, in that previous example, we could have written bless you.
Oh shoot, sorry, thank you.
Right, so let's pull this up. So in this example, our coefficient matrix or our augmented matrix corresponding to the system of linear equations is going to be 1, 3, 6, 25. Second row is going to be 2, 7, 14, 58. Third one, 0, 2, 5, and 19. So this is our augmented matrix. For the previous example. And just a quick word on dimension. So this is what we call a 3 by 4 matrix. Again, it's always going to be row by column. So 3 rows, 4 columns. Now, let's talk about row echelon form. Row echelon form has 3 properties. We're going to have 0 rows at the bottom. So any row that is entirely consisting of zeros is always going to be at the bottom. The leading entry which is going to be the first non-zero. So reading from left to right. So for example, here in this row, the leading entry is 2 in the second column. Leading entry is 1, leading entry is 2, both of those in the first column. So we want the leading entry of any row has to be to the right of the row above. And moreover, we want the leading entries all equal to 1. So our row operations, or excuse me, our operations, our elementary operations, correspond to row operations on the augmented matrix. I don't want to write those out again, but what do I mean by that? If we can pull up our notes page. We can switch the order of equations. That just means switching the order of the rows. I can take one row, move it up and down, and just flip them if we want. Multiplying by a non-zero means I could just take one of the rows and multiply by a non-zero scalar if we want. And then, of course, our big one, replace a given equation with the sum of itself plus a scalar multiple of another, means what we're going to be doing is taking a scalar multiple of one of the rows and adding it to one of the other rows, and then replacing that row with the result. So the operations we did were, well, our first step was to get rid of this 2. We want to first start off, we want to look for putting things in row echelon form. So what is row echelon form? Our leading entries all need to be 1. And if I look at the leading entry and go one row above, this leading entry should have started over here. So we can't have, this row has a leading entry in the first column, which means all the rows below it have to have zeros in that column. So our first step to get rid of this 2 is what we performed. So we did row 1. We did, sorry, minus 2 times row 1 plus row 2. And what do we get? So I'll go ahead and replace it. So we had our 1, 3, 6, 25. I know that I'll have a 0 here, and then 1 there, 2 here, and it was 8 here. And so this becomes our new matrix, our new augmented matrix for the new system of equations we had after our first step. So now we go through and we take a look. Well, here's leading entry is 1. And this one, the leading entry is 1 again in our second column, which means in the third column, I need a 0. I need zeros all below those ones. So that means I need that 2 to be a 0. How do we get rid of this 2? We now take minus 2 times row 2 and add it to row 3. And so we're going to have 1, 3, 6, 25, 0, 1, 2, 8, and then 0, 0, 1, and then we had minus 2 plus that guy gave us 3. And so this is our row echelon form. Now, from there, we simply solve the rest of the equations by substitution. We had our z is equal to 3 is what the corresponding equation is to this row. And then we ended up back substituting. What we can do instead is actually even take this process a little bit further in terms of row operations. And again, with bigger systems, more systems of equations, higher dimensions, this process is going to be a little bit easier than substituting every single time. So what we want to do is extend our row echelon form. Row echelon form we see is nice. We should have ones on the diagonal, or at least spaced out inward from the diagonal. Anytime we have a 1, all the entries below that are 0. So ideally what we would like to see is in this last row something like a 1 and then a constant. So that'll correspond to z is equal to 3, a solution to one of the coordinates. Well, how can we find the rest? We move it towards what's called reduced row echelon form. So reduced row echelon form is just row echelon form, which I'm just going to abbreviate REF, with one other condition, that the entries in a column above a leading entry are also 0. In other words, if we rewrite our example, we had 1, 3, 6, 25, 0, 1, 2, 8, and 0, 0, 1, 3. We first moved it to row echelon form. But ideally, in terms of solving a system of linear equations, we want each row to look something like this. This one corresponds to z is equal to 3, right? We want to correspond each of our columns and think of those as the independent variable, right? So this row, 1x plus 3y plus 3z equals 25. This one's nice, z is equal to 3. So after we put it in reduced row echelon form, we can actually still do row operations, right? If we do row operations, we are not changing the solution set. So I can actually get rid of the entries above these leading entries. So of course, nothing is above that 1, nothing to do there. But now that we have this leading entry as a 1 in our second row, I can get rid of the variables or the constants above that. And so now we kind of work from the bottom and move upward. So here we have a 1. So if we take row 3, multiply it by a -2 again, and then add on row 2, and we're going to replace that with our new row 2, what are we going to have? First row isn't changing. Now the last row isn't changing. And what's going to happen to our second row? I'm going to take this row, multiply it by -2, and then add it up. So this one's not going to change. -2 times 0 plus 1 still gives me that leading entry of 1 there in the second column. But now I'll have -2 times 1 plus that 2 gives me that 0 there. And then what's going to happen with our constants over here? -2 times 3 plus 8 gives me 2. Great, I've gotten rid of that 0, but all the entries we need to be 0. So we need to get rid of that one, and we need to get rid of that one. So let's go ahead and do now -6 times row 3 plus row 1, replacing row 1. So we are going to have a 1 here, a 3 here, since those zeros aren't going to affect anything. And now minus 6 plus 6 will give me a 0 in that column. And then minus 6 times 3 gives me minus 18 plus 25, changes that constant to a 7. We didn't touch row 2. And row 3 still stays the same as well. Great, so we've got zeros all above the Z column. And now we can get rid of this last one, the Y in the first row. Let's see if I can put both of those on screen here. So our last step, what we want to do is do minus 3 times row 2 plus row 1, and then that will replace row 1. So leading entry isn't going to change. We'll have minus 3 plus 3. We eliminate that. And since we eliminated all the Z's from both of those, we don't get any new Z's. And then we just have to mind the coefficients. So we had minus 3 times 2 gives me minus 6. And so we get 1 here. And so we have our solution. So this system of equations now corresponds to x equals 1, y equals 2, and z equals 3. And if you're paying attention, what's the first thing that pops out at you? Is we got a different answer. Or did we? Hang on. What was our solution to that problem? When we did it with row operations. Yeah, we did something wrong. So if we go back and look at what happened when we did our row operations, we found z is equal to 3. Why did we find y is equal to 6? Looks like we missed a minus sign somewhere. So what happened?
I think we did a different system of equations.
Did we? I'm pretty sure we started with the same one. Let's take a look real quick and go back through this. So we've got our augmented matrix, reduced row echelon form. Let me keep track of all my pages here. So here was our system of equations. We had 1, 3, 6, 25, 2, 7, 14, 58, 0, 2, 5, 19. So now we did elementary row operations on this guy to eliminate our x's, then eliminate the y's below. And then we went back and performed row operations to put it in reduced row echelon form. So our problem is that we make algebraic mistakes. So here, y plus 2 times 3 equals 8. Should have found our y equals 2. And then, of course, if y is equal to 2, we should have a 2 here and a 3 there. So we will have 18 and 6. So that'll give us a 24. So x is 1. So I was making mistakes doing this substitution and writing out the equations. More to write with these equations, right? Writing out these variables. Since the only thing that matters, again, we only have linear powers of each variable. So doing these elementary matrices helps you organize the work a little bit more in terms of what are the actual constants we're working with. So our first step, putting it in row echelon form, making sure we have 1s as our leading entries, 0s below all the 1s. once you get to that, we can put it in reduced row echelon form. And the process of putting it in reduced row echelon form essentially determines a solution for us. So just as a note of terminology, putting a matrix in reduced row echelon form is also called Gauss-Jordan elimination. Okay, so we've only got a few minutes. I'd like to do some more examples with these because we don't always get a common solution. So this just says that our solution is 1 point. 1, 2, 3. But as we saw at the beginning, geometrically, sometimes that always doesn't always work out. Sometimes there's no solutions. Sometimes there's infinite solutions. So we need to see some examples of how those work out, and then how do we write the solutions. We'll talk a little bit more about that tomorrow, I think, when we have time, or maybe we'll get started on one example here today. One thing I do want to talk about is the rank of a matrix. So for a matrix in row echelon form, the rank is the number of non-zero rows. So when we are putting things in row echelon form, sometimes it can happen that one of the rows essentially becomes all 0. The number of leading entries that are 1, you can essentially count, will give you the rank of the matrix. And then we have a theorem that the number of solutions, let me see, how do we want to state this? So if the rank of a matrix is equal to the number of rows, then there is 1 solution. If the rank of the matrix is less than the number of rows, let's see, number of rows, yeah, then there are infinity solutions. And then there's going to be no solution. So I got to be a little more careful about our definition. So for a matrix in row echelon form, the rank is the number of, not necessarily non-zero rows. Let's say the number of leading 1 entries. And then, so we've got to be careful about these last two. The first statement is correct. If the rank of the matrix is equal to the number of rows, we'll get 1 solution. So as we saw in this last one, our rank, we have 3 leading 1s for each row, or 1 leading row, 1 in each row. So our rank is 3 with 3 rows. Then we have 1 unique solution. If the rank of the matrix is less than the number of rows, and we should say and all rows are 0 below our leading rows, then we will have infinity solutions. We will have a parameter, 1 parameter, 2 parameter family of solutions most commonly seen. And then our last situation is if the rank of the matrix is less than the number of rows, and we have non-zero constants, below our leading rows, then there's no solution. So what do I mean by this? Sometimes when we're putting things in row echelon form or reduced row echelon form, we might actually end up eliminating, like if I have another row here and I eliminate all of the z's, I could have a 0, 0, 0, 0, and then a constant, like 0, 0, 0, 5. That row corresponds to 0 equals 5. So it doesn't make any sense. In other words, if we get mathematically contradictory statements, then there's not going to be a solution. We'll try to do some more examples like that tomorrow. We will have to move fairly quickly with some of those, because we also have to get into now generalizing these matrices and what sort of algebraic techniques can we do with these matrices. Any questions?